Hey, we have here on the board today another integral. This one's from MIT Integration Bee 2010. This was problem 21. We have the integral from 0 to infinity of dx over the square root of 1 plus e to the x plus e to the 2x. Okay, and to start with, what I wanted to do is something to factor this, and let's see how this is going to look. I'm looking at like a quadratic, like it's x squared plus x plus 1. And what I'm going to want to do here, I think what I'm going to do is factor an e to the 2x out of this. So when I rewrite this, it'll be e to the 2x times e to the minus 2x plus e to the minus x plus 1. Just noticing that if we multiplied e to the 2x back in here, we'd get exactly this. And then what I'm going to do here is I'm going to take this e to the 2x outside of the radical. Okay, then it'll be the square root of e to the 2x is going to be just e to the x. And what I'm going to do is bring it into the numerator as an e to the minus x. And I think the nice thing about that is this is going to be good for a u substitution, because what I'm going to do is I'm going to substitute, we're just going to call our u e to the minus x, knowing that this is going to work nice with the derivative. So let's see. Okay, so let's say that u equals e to the minus x, then our du is going to be just minus e minus x dx. Now if I create a minus sign in the numerator, I have exactly what we have here. So I think this is good. Let's do the substitution. So first for the balance, we'll plug an infinity in here. So e to the minus infinity, that's heading towards 0. Then we'll plug a 0 in here. E to the 0 is just 1. Okay, now, like I said before, our numerator is just going to be du. And then this is going to transform nicely to u squared plus u plus 1. Then I'll use this minus sign here to flip my bounds. Okay, now flipping it, now we're going from 0 to 1. And then what I want to focus on next is, let's just look at this here, and let's see what we can do to complete the square on this thing. So to complete the square, what I'll do is we'll start with our u, then noticing the coefficient here is 1. If we divide by 2 on that, it's 1/2. So the way I'll write it is u plus 1/2 squared. Then if you square this thing, you get u squared plus a half u plus a half u is 1u plus a fourth. We don't have a fourth here, we have 1, but if we add 3/4, now we haven't changed it. So now this right here is equal to this piece right here inside the radical. So I'm just going to rewrite it now in this form. So we're going to still have our bounds. Now for the 3/4, I want to write that as a perfect square. So I'm going to write it as square root of 3 over 2 all squared. Oh, sorry, I forgot a square right here. Okay. Okay, so now from here, you notice this expression is a little bit messy, but it's actually in the right form for a trig substitution. And what we want to do in this format where we have a square term plus something, I'm going to make my substitution. Let's make our substitution for this. We're going to call u plus 1/2 equal to square root of 3 over 2 tan of t. Doing that so that the square root of 3 over 2 works nice with this. Now I'll take my derivative. Okay, so derivative here on the left is just going to be du. Then we're going to have a square root of 3 over 2. Derivative of this is going to be secant squared t dt. And then before I continue, I want to solve for my t value here. So to do that, what I'm going to do first is we'll multiply by 2 square root of 3 on both sides, so that we'll have, let's see, we'll have 2 square root of 3. Like I said, it's a little bit messy. So 2 square root of 3 times u plus 1/2, and then we'll take a tan inverse on both sides. So t is going to be equal to tan inverse of all that. Okay, so now we'll make our substitution, and the bounds are a little bit rough just because of all the stuff we have going on here. So I'm going to take my 1 here for the upper bound and plug it in for this u. So plugging the 1 in here, this is going to be 3/2. So we're going to have, let's just see what we're looking at. We're going to have 2 times square root of 3, and then, well, again, 1 plus 1/2 is 3/2. So we'll have 3/2 here. A 2 cancels. 3 over square root of 3 is actually just the same thing as square root of 3. So we're looking at the tan inverse of square root of 3, and that's going to happen at pi over 3. So next we're going to take our 0 and plug it in here. That's just going to give, this piece is just going to be a half. Half times 2 square root of 3 is just 1 over square root of 3. So we're looking for tan inverse of 1 over square root of 3, and that happens at pi over 6. Okay, now next we want our du value. So our du value is going to be square root of 3 over 2 secant squared t dt. Then in the denominator, okay, so we got our big square root. U plus 1/2 squared is going to be, okay, so we're going to have square root of 3 over 2 squared tan squared t plus square root of 3 over 2 squared. But notice the square root of 3 over 2 squared, I can pull that outside of the radical because it's squared, right? So this can come outside as just a square root of 3 over 2, but then it's going to cancel with this. Okay, so let's remove this because we're factoring out from this term and this term, and this here is going to just be a 1. But tan squared t plus 1 is just an identity for, this is the same thing as secant squared t. So what's going to happen is we have secant squared t inside the radical. Square root of secant squared t is just going to be secant t. We don't have to worry about absolute value because we're all positive in this region. So this is just going to be 1 secant t over secant squared. So I'm just going to cancel this whole thing with one of these, and we're just integrating secant of t. Okay, so really good progress. We're all the way down to just integrating secant t. And we know what this is, very common integral. So this is going to be natural log, absolute value, secant t plus tan t. But again, I think I'm just going to remove the absolute value because we can see that we're in the first quadrant and everything is positive in the first quadrant. So I'm just going to remove this, and we'll just look at that as parentheses, but we need to evaluate from pi over 6 to pi over 3. Okay, so now we'll plug in. So we're going to have plugging in pi over 3. Secant at pi over 3 is going to be, cosine of pi over 3 is 1/2, but it's 1 over 1/2, so we're going to have a 2. And then tan at pi over 3 is just going to be square root of 3 minus, and then we'll evaluate at pi over 6. Secant at pi over 6 is going to be 2 over square root of 3, because cosine is square root of 3 over 2 at pi over 6. And then for tan at pi over 6, we could write it as square root of 3 over 3, but I'm going to write it as 1 over square root of 3. The reason I'm doing that is so that we have a common denominator here. Okay, so when we add these together, 2 plus 1 is 3. So this is going to be 3 over square root of 3. But then this is actually the same thing as square root of 3. And then just one last step, because we're subtracting, I'm going to use this property of logarithms to divide these two. So I'm going to rewrite it as 2 plus square root of 3 over square root of 3. We could leave it like this, but I'm going to just simplify again, or I don't know if I'm simplifying, but I'm just going to write it as 2 over square root of 3, and then square root of 3 over square root of 3. This is going to be a plus 1. That's it. Thought it was a good one today. So thanks everyone for watching. Please like and subscribe. Have a great day.